being here. We have a short introduction before starting the actual meeting, so bear with me for the following slide. They note well, so I think most of you are pretty well aware of that, but this is the IETF follows the IETF intellectual property right disclosure rules, and so by participating in the IETF, you agree to follow the IETF processes and policies that are listed here, and we invite you to have a close look at this recommendation and the definitive information provided here. For the audio and video recording, so the IETF routinely makes recordings of online and in-person meetings, including audio, video, and photographs, and publishes those recordings online. If you participate in person and not choose to wear a red "Do Not Photograph" lanyard, then you consent to appear in such recordings. And if you speak at a microphone, appear on a panel, or carry out an official duty as a member of IETF leadership, then you consent to appearing in recordings of you at a time. If you participate online and turn on your camera and or your microphone, then you consent to appear in such recordings. For the privacy and code of conduct, as a participant in or attendee to any IETF activity, you acknowledge that written, audio, video, and photographic records of meetings may be made public, and the personal information you provide will be also handled according to the privacy policy that you can find references here in this slide. Short statement on the goals of the IETF. So the IETF conducts research. It is not a standards development organization. The Internet Research Task Force focuses on long-term research issues related to the Internet, while the parallel organization, the IETF, focuses on shorter-term issues of engineering and standards making. And while the IETF can publish informational and experimental documents in the RFC series, its primary goal is to promote the development of research collaboration, teamwork in exploring research issues related to Internet protocols, application architecture, and technologies. And you can get more information about the goals and missions of the IETF in the an IETF primer for IETF participants, RFC. The online meeting etiquette, so this session is being recorded. Please keep your audio muted and video off when not presenting or speaking. And when speaking, please start by stating your name. A few useful links, you can also find that on the IETF meeting agenda. So the links to the materials, the Meeteco sessions, and the meeting notes. So for today, we have a very dense agenda. We have 2 hours meeting, but we have a lot of topics to cover. So our first request will be for presenters, please stick to the time allocated, not more. We would like to have time for question and answers. So bear in mind also when you're presenting to keep time in your presentation to address questions that you will have. Do not use all your slots just for presenting your slides. So we will start with this current introduction and research group status. Then we will have a guest presentation and a number of topics on network digital twin, green networking, artificial intelligence, and intent-based networking. I'll not go through the details because we want to save a bit of time here. Just a quick status on some activities of the research group. So we have research group documents in the pipe. We have 2 documents that are with the RFC editor, currently in the edit stage. So the RFC editor is looking into those documents, and we expect to get some feedback soon on the next steps. We have 1 active research group document, Digital Twin Network Concept and Reference Architecture, and we will have an update on the progress of this draft in this session. And we have also another document, Network Measurement Intent, one of IBM use cases that has been in first call for adoption. And we ask for a revision, addressing some comments received to make a second call for adoption. And we will also have updates on this document in this session. An outlook for future meetings, but this is a bit business as usual. We will organize some interim meetings or follow-up discussion on the different topics. We have 1 in the pipe that we try to organize for some time on the design, deployment, and operation of distributed AI. We have also some presentation today about this topic, but we would like to offer a later platform to address this topic in a dedicated interim or collocate with a research conference. We have a network digital twin side meeting this evening in the Philadelphia South room. So just side meeting, and it's not an official meeting, no agenda. We can also organize follow-up discussion on IBM use cases. So Also, we are open to receive your inputs for further meetings. This will be for interim ones, but the next, let's say, plenary meeting we aim for will be with IETF 115 in London in November. And that's it for the introduction. I invite you to go now to the next step in the agenda. And I invite Felipe to come to the stage to present.
Good morning, everyone. My name is Felipe Lopes. I'm a lecturer and researcher at the Federal Institute of Alagoas in Brazil. First of all, I'd like to thank Yerma and Lord for giving me the opportunity of presenting this work here today. Before I start, I will try to, let me just put it in mute mode. I need to break the protocol a little bit. I don't know if you see that there are so many Brazilians here today, so I'm not here by any support of the Brazilian government. I'm here just for the support of the Future Ray company that provided the order at the Brazilian Congress of the Computing Society. And yeah, and for denunciate or denounce the neglect that's occurring in Brazil right now in science and research and education. So my presence here is not due to with the support of the Brazilian government. So, well, starting talking about the paper entitled Using the RFC 7575 and Models at Runtime for Enabling Autonomic Network in SDN. It was awarded at the workshop pre-IETF last year. It is part of my PhD thesis that I defended in 2020 by the Federal University of Pernambuco, also in Brazil. And I'll just present part of it. If you want to see more details, we can discuss later. Please, next one. Well, before talking about the paper itself, we need to remember or to introduce you about the concept involved in it. The autonomic network management, as may you know, we have in traditional management, in traditional network, we have this autonomic loop put above the data plane where you need to define the business goals, we need to define the knowledge generation, we need to define how the policy process will occur, and also the information process. The thing is, how can we translate or to insert all of these components, all of this policy processing, the business objectives and stuff in the data plane? This architecture here, it's not new. It's the Foucault architecture based on Strassner. It's from 2006. And it just defines how this autonomic loop can be coupled with the data plane. The next. Well, when we consider the SDN network, the SDN architecture, obviously these business goals, the policies, the knowledge generation, the policy processing, it now needs to communicate through the control plane. And for communicating with the control plane, we need to translate these business goals into network rules. Excuse me, can I remove my mask? Yeah. Okay, so besides translating this policy and processing and the business goals, we also need to represent the context from the network, from the control plane to the layer above, to the autonomic loop above. So the question is how to enable autonomic network in SDN, in an SDN architecture. Well, it raises so many challenges as the recent internet draft entitled Research Challenge in Coupling Artificial Intelligence and Network Management of Harriman. And we can see several opportunities as well. Okay, for introducing the RFC 7575, for those who are not aware about it, it just defines some guidelines. And it's like a reference model. If you want to achieve an autonomic management in networks, not in SDN, you can follow these guidelines to achieve design goals, to try to implement your autonomic management in your network. So it defines 4 self-start properties, like the self-configuration, self-healing, self-protection, and optimizing. Besides, it also defines 11 design goals. So if you want to provide your full cycle of autonomic management, you need to implement or achieve each of these goals following these properties. So, okay, we have the concept of autonomic networking. We have the RFC guiding anyone who wants to implement it. And the question again is how to enable autonomic networking in SDN. We have some guidelines. We have the concept of autonomic networking, but how to implement it? How we enjoy this? 2 different areas together. We know that autonomic networking is not a new area. The first research papers comes from the 2000 year. And we know now that the control plane is software. And we also know that there are related areas in computing, like software engineering, that can provide some specific concepts about autonomic software. So if you have this autonomic software, I don't know if, okay. If you have this autonomic software, you will have the concept named from the software engineer. You have the models at runtime concept. The people from other related area provided a concept that may help us to think about or to have some, not so new ideas, but related ideas to how to implement our autonomic networking management using the control plane as software. Okay, so this is the concept, the black circle here, models at runtime that we are using in our approach, in our proposal, to demonstrate how this combination between the RFC 7575 and the autonomic network management concept can be combined together to provide such an approach. Obviously, the IETF's community also made these several contributions into the autonomic field. So, continually checking or observing other related areas like the software engineering community, we have class diagrams, we have UML, we have sequence diagrams. If you look for the database area, we have the entity relationship diagram, we have UML. So in machine learning as well, we also have models abstracting the complexity below and providing some high-level models for the users and developers to evolve the solutions, to discuss the solutions with, for example, in software engineer, you can discuss your solutions with clients, with developers, stakeholders, and so on. In networking, we can have topologies, we have a Yang model, but is it easy to visualize the models? How can we define intents in there using them? How to grant the correctness between these models to check if there is no inconsistency between the logic of the software that you're trying to implement. And obviously, how can we use Yang or netconf to enable 0 or 1 touch with or without human touch from these models. So we now need to introduce the main concept that is in the core of our proposal, that is the models at runtime. It comes from the software engineering community, and it defines that any system, if it's a network or a control plane running some software, it defines that any system has goals, has behavior, and has structure. And if you are going to going deep into each of these parts of the system, you need to visualize that it needs to monitor, you need to execute some action, you need to analyze each action that you're performing. We also need to separate or to organize these systems in 3 layers: the objective layer, the configuration layer, and the base layer. So we have the concept how to visualize any system to provide autonomic behavior, but how can we implement it? In fact, we need to, according to Asman, an author that research about models at runtime, we need to define meta models at first, because it's using these meta models. If you look for the left picture with some yellow boxes, you need to define these meta models to provide them formalism for your language, for your modeling language. You need to define how you can associate each concept, for example, objectives and actions and flows. How are they connected to each other? We also need to define a concrete and syntactic syntax to provide to the user or the network operator elements so he can model his objectives and model his network capabilities, and so on. Besides that, we also need code templates. We need to have these code templates to make adaptation and the execution of the system. You cannot just provide for the user some interface, and the user will try to program it directly if you are trying to model objectives. You need to provide to him some abstraction. And also we have monitoring techniques and machine learning algorithms combined together to try to achieve the adaptations, to try to execute or achieve the modeled objectives as well. So in our proposal, we used the RFC 7575 as a north, and we provided this 3-layer architecture, which is composed of the network model layer at the above. We have the adaptability layer in the middle, and obviously we are using the SDN architecture at the infrastructure layer. The network model layer, we have 5 models. We have the configuration model of the network, we have the capabilities model, and obviously we have the objectives model, where the user or the network operator can define his objectives in a high abstraction level. Giving some details about each of these layers, the first one, the network model layer, we need to use the previously mentioned meta models. We defined these meta models. For example, here we are having at the middle the meta model for defining the objectives model. So we formalize how you can define the objectives, how you can associate these objectives with actions in your network, how you can associate these actions with flows, and so on. At your right side, we are seeing the meta model for the applications and for the packets and the traffic that you also can model in your high-level tool. If you look for your left, you have the concrete syntax at above, and you have the objectives models using the concrete syntax. So you need to understand these two things. We have 2 meta models, and we have 2 concrete syntax being used in this slide here. Next one. In the middle layer, we are using a deep reinforcement learning algorithm. So it is using the information of the models from the objective layer as inputs to this DRL algorithm. So the parameters, the network parameters, the discount factor that this DRL algorithm is using, and they are being used from the objectives layer. But it also is monitoring the network in the infrastructure layer. It's really important that we see that the DRL algorithm and all the code are just generated from the high-level models. You don't program it directly. The code of the DRL algorithm are generated from the above layer. So you can look for this layer and see that we have a knowledge base that keeps learning according to the actions executed at the network with the decision that is randomly decided and executed by the algorithm. And according to the execution of each action, it can verify if is the decisions being more close to the model objectives, or if the decisions that are being chosen are making the network parameters worse compared to the model to the objective to be achieved. Next one. So the discussion to bring to here is that as we have the clear conceptual difference between intent, policies, and service models, as the Internet draft, intent-based network, concepts and definition, we can discuss if the proposed MART approach, if this model at runtime approach is a feasible way to implement these abstractions and these concepts. And if could the ARC architecture can have this new abstraction level using these models to create the modeling and translate these models into network code. And the last thing that I bring here to discuss is that if or how intents will be translated into network code or network rules, how they will be integrated with the monitoring and the adaptation rules and actions. So a mark-based definition, a mark-based approach may help in this case. Okay, concluding, we just saw this proposal for enabling autonomic networking management in SDN. We saw how the combination between different areas of knowledge can be combined to provide some new solution. We also see briefly high-level modeling architecture for implementing this autonomic networking. And we just saw the discussion that may occur so far. Well, just to acknowledge the supporters for me that I'm being here today, the Future Ray that is provide the travel grant, the Federal Institute of Alagoas that provided me the agenda to be here, and also the Laboratory of Data Engineering and analyze where I do my research. Thank you very much.
We have time for questions or comments. Okay, so if there are no questions, thank you again, Felipe. We can. Okay. Okay.
I'm sorry, Diego Lopez, Telefónica. What I was wondering is precisely these smart models, how complex would be to derive them from the normal specs we have or from the normal goals, because, you know, I have no doubt that once you have this in place, it would be useful. The problem is how long it would take to have them in place when you need to monitor a service, define a service, or what is your experience, or whether you have any kind of metrics or something like that about the process.
Okay, if I understood you correctly, are you asking about the performance of this model?
No, I'm talking about the learning curve, how much for someone. Let's say we now go and try to define a service based on SRv6 that is so in fashion and connecting several points, and how much would take to apply these and make an analysis, because at the end, if you have to derive this from protocol by protocol, it seems a little bit lengthy.
I think I understand now. Well, as we have like a layer or a meta model that abstracts the complexity. We are not protocol oriented. We can generate the network rules for any protocol. So for example, you can model your objectives model, okay? So after you model it, it can generate code for OpenFlow, it can generate code for P4, it can generate code for any protocol. So it's the learning curve, if you mentioned it right, the learning curve is just to know how to connect the boxes for defining what's your objective. For example, if you want...
But you need the meta model to start with, right?
The meta, you don't need to create the meta model. Actually, the network operator doesn't need to create the meta model. He just needs to use the model above, the concrete syntax. It's like a modeling language, like a UML or class diagram. But for having this class diagram, do you agree that you have a meta model describing it, right?
Okay.
So it's a model that has a meta model describing it. So the meta model itself, yes, we need to develop for each case, like the objects that you need. But after defining it, the network operator or the network developer, he just needs to use the concrete syntax, like creating his class diagram if you are a software engineer.
Yeah. So, yeah. Okay. I think I understand. I had to look in a little bit more detail. Well, thank you.
Okay.
Thank you.
I invite you to maybe continue the discussion offline after the session. We have a very tight agenda. Thank you, Felipe. I think there will be follow-up discussion after the session. Thank you.
Thank you.
Our next speaker will be Sheng Zhu for the concept and reference architecture draft.
Hello, chairs and everyone.
Yes, we can hear you.
Okay, this is Chen Zhou from China Mobile. Today, I will present the draft update of digital twin network concept and reference architecture on behalf of our co-authors. Next slide, please. The draft was adopted by the research group in March this year, and the major change in this version is to add new sections of enabling technologies to build digital twin network to reply the reviewers' comment, actually, and including data collection services, network modeling, network visualization, and interfaces. The coming slides will show the brief info on the four enablers respectively. Next slide, please. Okay, first enabler is data collection and management. Regarding data collection, diversified tools can be used to collect various type of data, including legacy tools of SMP, netconf, IPFix, telemetry, INT, etc. And also some innovative tools like sketch-based measurement, IFIT, flow information telemetry, IOM, and in-band flow learning, etc. Actually, we have submitted a dedicated new draft regarding data collection. I will give instruction later. For data management, data warehouse tag, fast search, batch data handling, conflict avoidance, and unified interface for data exchange should be studied further. Next slide, please. Okay, network modeling is the most important enabler to build digital twin network. This slide shows a brief summary and a comparison for several major modeling types. The first type is simulation or emulation, such as NS2, S3, OPNet, MiniNet, EVE, NG, and GNS3. The second type is virtualized technologies using NFV, containers, etc. Microsoft's CrossNet and Aresta's Cloud Vision Portal, CVP, are successful examples here. We know the first two types of modeling methods are easy to deploy and suitable for, especially suitable for functional and protocol validation. However, they have limitations of including high resource consumption, poor performance analysis ability, and poor scalability. A third type is modeling using mathematical abstraction. Here lists three typical methods, include formal methods or formal validation or verification, theory of bottleneck structure, and data-driven AI machine learning algorithms. Each type has some example solutions listed in a table you can see. And mathematical models are of low resource cost and fast calculation, and especially suitable for large-scale network. However, we think those have some limitations on extensibility and lack of ability on functional and protocol evaluation. Specifically, AI machine learning models have low interpretability and also need relatively expensive data for training. Since each type of network modeling has both pros and cons, we believe that multiple methods can be in combination to build a comprehensive digital twin network system. Next slide, please. Among all methods, data-driven methods modeling.
You will have to speed up and move to the next slide, to the next presentation pretty soon, please.
Okay. Okay. Among all methods, data-driven network modeling is whole research direction. This slide shows a digital twin modeling survey from data-driven performance modeling perspective. So for more details, you can refer the print paper. Next slide, please. Okay, for network visualization help users better understand the internal structure of network and mine valuable information hidden in the network. This slide lists candidate techniques for network topology visibility, modeling visibility, and interaction methods respectively. Next slide, please. This slide shows the three types of interfaces to build a detailed system based on proposed architecture. All interfaces should be open and standardized. Specifically, northbound interfaces should be extensible, and candidate options can be RESTful and RESTconf. Internal interfaces should be fast and efficient. Candidate options can be XMPP and HTTP3. Southbound interfaces should be lightweighted. Candidate options can be SMT and NetConf. Next slide, please. Okay, in the future, we will dig deep on each enabling technology, and we'll build a digital twin network system on trial network and validate and the gains against specific use cases. We also work on proposals to enhance the document. Thank you.
Okay, Sheng, I suggest you go to the next presentation right now, and we will address questions at the end of the slot, please.
Please keep it concise in 3 minutes, the presentation.
Okay. This is here. I will present the draft update on data collection and requirement the data collection requirements and the technology for digital twin network. Next slide, please. The scope of the draft includes describe requirements and data collection and for building digital twin network, and to provide the data collection method towarding build digital twin DTN data repository. The objective of this draft includes identifying the data collection requirements and principles for DTN, and calling for more efficient data collection methods suitable for DTN system, and reach a consensus on selecting data collection method for various network data. Next slide, please. Initially, the draft was just a specific data collection method for digital twin network. Now we promote the draft to extend the scope and to general data collection requirement and the methods for digital twin network. So in this version, we rescope the draft and we add sections of data collection requirements for DTN and refine text and make some editorial changes. Next slide, please. Okay, this slide shows the content of current draft. Next. Okay, draft list 6 data collection requirements. So in brief, the first is the data collection should be target-driven and on demand. The second is to use diverse tools for various data. And especially here, we list some new Nmrg directions of that are worth of studying further. The third requirement is lightweighted and efficient collection, and some detailed requirements list here. Next slide, please. The fourth requirement is open and standard interfaces for data collection, and the fifth requirement is naming for caching, and the last requirement is the efficient market destination delivery. Next slide, please. In this draft, we provide an efficient data collection solution for digital twin network. Current collection method mainly collect raw and full data from physical network and have problems of time cost, insufficient storage resources, and low computational efficiency, waste of bandwidth resources caused by data transmission. So this draft proposes an efficient and lightweight data collection, aggregation, and correlation method. First, twin network sends instruction to physical network to collect data on demand. Then physical network completes instructions such as knowledge representation, and the next telemetry streams element TSE of physical network completes data aggregation and correlation. Finally, TSE sends the representation data to the twin network. This is a short procedure. Next slide, please. This slide shows the detailed data collection procedures of the method. You can refer the draft for more details. Next, please. Okay, going next, we will further investigate and categorize the legacy data collection tools toward various data for building DTN system, and we will verify data collection method on DTN demo system, and we are coding for more efficient data collection method suitable for digital twin network system to enrich the draft. Looking forward to comments, stretch, and questions. Thank you.
Thank you, Sheng. I mean, due to time limitation, we will take questions offline or in the chat. Thank you for the presentation. These are interesting new drafts that you're presenting, and we welcome any feedback on those two drafts. Thank you, Sheng.
Thank you, Chair.
Our next speaker will be Jordi. Can you come here? I mean, you don't need it. I can switch the slides for you, or you can do it on your phone. You can start.
Hi, I'm Jordi Pellicer, from UPC Barcelona Tech, and well, representing this draft about a digital twin for network performance. This is joint work with all these people from Huawei and Telefonica Research. Next, please. Next one. Sorry, have this. So, well, very briefly, that because we already know more or less the concept of a digital twin, it's a virtual replica of a physical system, and it recreates with high fidelity the behavior of the digital system. No? Like the example that most people use are, I don't know, I want to build a plane, but I don't want to build a plane, so I use a model to understand how the wind will affect some part of the wing. Next, please. And in our case, we're proposing a digital twin, but only for network performance. So the input of the digital twin are a complete description of a network, or as complete as the user wants, and output are performance metrics. Going more into detail, when we refer to different, here. When we have the input, we're thinking of, when I say a complete description, I mean the topology, routing configuration, if you want some specific scheduling policies, if you are using some, if you need a specific traffic matrix, or you have specific flows or different traffic models. And the output right now, we are targeting 3 metrics. So that is the delay, jitter, and losses. We think that these are really important because are the ones that are more widely used in network management. For example, in real-time applications, you're always interested in the jitter of a voice call, or in online gaming, people always worry about the delay that they have. Next, please. And in the draft, we start talking about the requirements of this digital twin. Next, please. So the first requirement is that it should be fast. Next, please. Because, well, we are also targeting network optimization scenarios. By network optimization, we are thinking of these algorithms that explore a lot of different configurations until they find an optimal one, or a configuration that satisfies a certain objective. And if you want to run these algorithms in more or less real time or short time scales, you need a model that is really fast. Of course, a digital twin has, for network performance, also has to be accurate, because you need certainty that the performance will be within predefined error range. It also has to be scalable. Next, please. Well, because usually production networks are much larger than any testbed that you can use to test how your model works. And well, exactly because of that. And as I said before, it should support a wide range of different types of network. I said different routing configurations or routing protocols, scheduling policies, and also different ranges of traffic intensity. And finally, it has to be accessible. Next, please. And by accessible, I mean, on one hand, being able to communicate with existing systems. So it needs a way to plug into an SDN controller or different control and management systems that are present in current networks. And it also has to produce metrics that are commonly used in network engineering. No? So, for example, I said before, delay or jitter, and not, some models produce some outputs that are not easy to understand for network engineers. Next, please. And in the draft, we outlined the architectural interface of this digital twin. Next, please. And we are following the architecture of the reference architecture of the digital twin concepts draft. And well, in actually, you can see here, now we have the physical network, then we also, that is connected to the management and control plane. And also the digital twin is connected to the management and control plane. We have also outlined the interfaces here. Next, please. And well, the configuration interface and the measurement interface, we have seen previous drafts that talk about how to collect data. We can also leverage widely used IETF protocols like netconf or netflow for measurement. Next, please. And this administrator or this intent-based interface, for our use case, minimally, it should just support running the digital twin, defining some optimization objectives, applying some configuration. But of course, it can range from a simple CLI to a state-of-the-art graphical user interface, or even this more modern intent-based networking that there are some drafts in the group also. Next, please. But the one that we're more interested in discussing here with the research group is the interface of the digital twin, because basically it's the one that is not that clear. And from our perspective, this should be like a request response interface, and you send as inputs the inputs I've said like 3 times before, the topology, routing configuration, the traffic demands of your network, and then you get an output, 3 matrices with the performance metrics like the delay, jitter, and loss. Next, please. But we think that this requires more discussion. For example, maybe you want multi-vendor compatibility. You want to use a digital twin from a specific vendor for some tasks, or maybe you need then to swap it for another digital twin from another vendor. Also, we don't really understand which control plane element should we connect. Should we connect to an intent-based interface? Should we connect to an SDN controller? And also, I said that the type of interface should be a request response, but maybe you want the publish subscribe model in which you are continuously evaluating the performance of the network because you want to adjust in real time some performance parameters. Should we include inside the digital twin the validation of the SLA? So just, like a Boolean telling you, okay, the SLA is okay, it's not okay. Or maybe this is usually something done in the management plane. Next, please. And finally, well, I have quick notes about the implementation. Next, please. Well, we already presented this table in the previous meeting, so I'm going to go very quickly over it because also we more or less saw the same in the previous presentation. No? So the first thing you consider when you want to build digital twin is say, okay, maybe you can do it with simulation, and because network simulators are very accurate, and also they support virtually any feature, and if they don't support, you can implement it. But the key point is that they take a lot of time to run. For example, we've said that like 10 gigabits links can take like 11 hours to simulate. And we said that we would like a digital twin that is fast to perform network optimization. The next you could think about is queuing theory models because they are super fast and they can provide reasonable accuracy. But there is consensus on the research community that they suffer from accuracy when you have realistic traffic models like TCP or equivalent. And finally, we had to look at machine learning models. And well, we tested different machine learning models. And our conclusion is that graph neural networks, that are a kind of neural networks that are able to understand graphs, are the ones that offer outstanding accuracy. Basically because, I mean, the input is a graph, so they naturally render to this nice performance. Next, please. But why I'm talking about implementation in a research group? Well, if we are about to work with machine learning, well, it's a continuously developing technology. It's really complex, and there are some limitations that are different from what we're used in networking. No, so I don't know. Maybe you have a switch, and you know that the backplane goes at 1 terabit, and you can do your calculations more or less. But for example, with machine learning, well, everyone knows that it needs a lot of data to train. Maybe you cannot, you don't have this data. Maybe you have some legal limitations on obtaining this data, or it's from a customer and you cannot ask your customer data. And also another interesting point is that usually machine learning models cannot predict what they have not seen. So if I have a model and I haven't trained it with samples of a network that is congested, it will never, ever tell me that my network will get congested. And this is not really useful. And in order to understand also all these limitations, we implemented a performance digital twin prototype that is called RoundNet Erlang, and it's based on GNNs, and we have open sourced here. You can get it on GitHub. In order so that people know more or less the limitations and play with it and understand the limitations of this technology. I think that's all.
We have 2 minutes.
Yeah, we have time.
So if there are comments or questions to Jordi and the co-authors. I mean, I'm sure since the network digital twin topic will be under also later, next presentation and this evening, there will be a lot of questions for follow-ups, but thanks. Okay, our next speaker will be Dan Yang or Hongwei.
I think it's done then. Online, I suppose.
Okay, Dan Yang, you can start your presentation. You have 5 minutes for twice, so you can, I mean, take 10 minutes to go through the presentation. Thank you.
Okay, can you hear me?
Yes, we can hear you well.
Okay, then I will give a present about the 2 drafts intent. And the next slide, please. And the first one is about the digital twin network flow simulation. You know, some important application scenarios of the digital twin network all require the virtual flow in the twin network to accurately simulate the real flow in the physical network. For example, network new technology experiment, network configuration verification, network performance optimization, and so on. So how to accurately simulate the real flow is a question. And to solve the problem, we proposes the following methods to realize the high fidelity simulation of the physical flow by the twin flow. And it also needs to satisfy the satisfying the following three characteristics at the same time, which can be concluded as the three consistent. The forwarding paces are consistent means that the twin nodes that twin flow passes through at the twin network layer are consistent with the physical nodes that physical flow passes through at the physical network layer. And the second one is that means the twin flow and the physical flow have the same performances as the network delay, packet loss, and jitter. Data characteristics are consistent means that the data packets of twin flow and physical flow have the same key characteristics. And next slide, please. So as shown in the animation on the right, please play the animation. The most perfect twin flow satisfies that the data forwarding pace, forwarding time, and the flow data are exactly same with the physical traffic. Please help to play the animation. Thanks.
Daniel, I'm sorry, but this is a PDF, and I think the animation is not playable right now.
Okay. However, this is obviously impossible because data collection takes time and the package by package is too. So how should we implement the simulation of the twin flow? We think that it needs to satisfy the three key technologies. First is that the physical network element and the twin network element have unique identifiers in the entire network. Second is that the data transmission network between the physical network and the digital twin network are using the DNet networking. The third is that only the key information of physical flow is collected. So some payload information doesn't need to be collected. So next slide, please. So this page gives the advantage of the proposed simulated methods. The first one is that the forwarding pace, forwarding time, and key flow information are consistent between twin flow and physical flow. And it can meet the needs of various scenarios. And what's more, is easy to implement. Next slide, please. Then is the second draft one-way delay measurement method based on digital twin network. And this one is based on the last one. So as we know, traditional network delay measurement methods are including active measurement, passive measurement, hybrid measurement, and so on. But all these measurements have some disadvantages, such as it requires special test packets and time synchronization, and cannot test all network protocols. And it needs to change the format of service packets. So there will have some problems in actual deployment. And we propose the method to solve this. And it can realize that no need to send measurement packets, no need to change the physical network configuration, no need to change the format of service packets, and no require physical network elements to support the time synchronization protocol. So next slide, please. So this page is about the specific solutions. First, according to the digital twin network architecture, we can build a digital twin layer, including twin network elements are corresponding to physical network elements. Then maintain the time synchronization between each twin network element in the digital twin layer, and it can be two cases. First one is if multiple twin network elements are in the same physical entity, such as the NFV-based modeling methods, where multiple twin network elements are deployed in one server and share the same local clock. The twin network elements themselves is time synchronized. The other one is that if multiple twin network elements are deployed in different physical entities, use PTP or NTP to achieve time synchronization between physical entities to ensure the time synchronization of all twin network elements. And the data transmission from the physical network layer to the digital twin layer will use a delayed deterministic network to ensure that the data transmission delay between each physical network element are the twin network element is deterministic and or precalculable. So when a flow of the physical network is input from the physical network element one, you can see the figure in the right. When a flow of the network physical network is input from the physical network element one, passes through the physical network elements 2 and 3, and finally is output from the physical network element 4. And when physical network element 1 receives the data package, it will normally forward the data to physical network element 2 and transmit the data to twin network element 1 at the same time. At this time, the local time of the twin network element 1 is can be seen as a little t1, and the deterministic network transmission delay is a big t1. Then the arrival time of the traffic information recorded by the twin network element is the little t1 minus the big t1. Similarly, the arrival time of the data packet recorded by other twin network elements is little tn minus little tn, little big tn. And next slide, please. Then according to the arrival time of the data package at the twin network elements is one-way transmission delay between physical network elements can be calculated. So for example, if a UDP data package is transmitted from physical element network element 1 to physical network element 3, the one-way transmission delay is as follows. And under the premise of time synchronization between twin network elements, the transmission delay of packets of any protocol type in any two physical network elements is equal to the following formulas. So as a conclusion, time synchronization between physical network elements is not required during the measurement process. And the accuracy of delay measurement depends on the time synchronization accuracy of the twin network elements and the time synchronization accuracy of the delay deterministic network. So if both use the PTP synchronization protocol, the delay measurement accuracy can reach the nanosecond level. So next slide, please. So for next steps, we will strengthen the realization of system solutions and verify program performances, and we also welcome proposals to enhance the jobs. Thanks.
Thank you, Daniel. We have people in line. Alex, first, please.
So, thank you. I have actually a fundamental question. Could you explain a little bit the motivation for this? I did not quite get that. Well, one thing basically is, I'm not sure if basically within a digital twin network, you would actually have twins of every flow or of every packet. And so maybe you can explain a little bit that. And the second thing is, why would you not just perform the measurement in the production network as opposed to in the digital twin? Who is concerned with the measurements in the digital twin? Really, actually, you want to have the actual thing there. So maybe you can explain a little bit better why or what is motivating your work. Thanks.
Okay, thanks for your question. And we think that by this way, we can get an accurately flow simulation, and the delay can be measured can be measured and the physical network is not changed, and it's just take requirements for the twin network, and it should not need the physical network to be time synchronized.
Okay, so maybe just sorry to clarify, perhaps what can you do with this that you couldn't do if you were just measuring in the actual network? What's the additional value, I guess, you have by measuring on the digital twin?
Maybe just for the sake of time, Daniel and Alex, please address the question offline on the mailing list or directly, please, because we have also other people in the queue. So Albert and Dean.
Yeah, hi, this is Albert from UPC. So I have a similar question as Alexander, right? So I don't really understand. So if you can measure the real thing, why do you need a digital network? Now, this brings me to two actual questions. The first one is, it seems to imply your drafts that you need the same amount of resources for the digital twin than for the physical network. That's the first question. I don't know if that's correct or not. So the digital network is actually a network of routers which are pretty much doing the same thing as the physical network. Is this correct?
Yeah, yes, the main reason is that the physical networks are not affected, and we just we just measure in the twin network layer.
Okay, understood. And my second one is rather a comment, and I would like to see your understanding. I have a feeling that we have like a requirement on digital twins that we never put explicitly, but somehow we understand digital twins as something that will tell me what will happen if I change something on the network, if I have a certain traffic, but it's not, it's more about the future and what if scenarios rather than what is happening in the present, because in the present I already have my physical network. I don't know your view on that. I didn't put very well this requirement. I don't know how to express it, but I don't know if you have an opinion on that.
Okay, we can have more discussions offline, and we think it's not, it can't be simple, give a simple explanation.
Okay, thank you.
Okay. Thanks a lot, Daniel, for the presentation. I think there are some interesting questions to address to clarify some aspect of your proposals, and I invite the discussion to continue offline on the mailing list or directly between the participants. Thanks again. So in the agenda, we were planning to have a quick wrap up on the network digital twin activity proposed in the Nmrg. So the goal here is, in fact, we have received more proposals, more inputs on this topic in the Nmrg in recent time, in the past few months. So we see that this is a growing topic of interest, not only in Nmrg, but also in other communities, other groups. And this is why, in fact, we invite people to attend, if they can, the side meeting that we have this evening, but there will be also follow-up discussion on the mailing list or by other means. The goal is, in fact, to understand a bit the future direction of these different proposals. Nmrg could be a forum for some of the discussion. It's a research group, so we want to focus on these research activities. We see that there are other proposals that are more towards standardization or engineering or even implementation, etc. So these are very interesting proposals. What we would like to clarify is, in fact, in the scale of IRTF and IETF, what could be the landing spots for this activity, depending on the type of activity, and also maybe to share information and coordinate with what's happening a bit in other groups and in the research community. So this will be some of the points we would like to discuss later on in the side meeting, and again, to make it available to anyone also on the mailing list. So this was just to wrap up a bit this discussion. Thank you, everyone. We are now switching to another topic of the agenda, which is on green networking. We have two presentations, also a new draft have been proposed in different, for IETF, RTF, and the first presentation will be from Alex.
Okay, thank you. So yes, so this presentation is basically on a potential new topic to look at here in the scope of Nmrg. And this concerns the topic of management for green or also, well, sustainable networking in general. There are two associated drafts with this. So there's challenges and opportunities in green networking. I think this one is specifically actually suitable for discussion in Nmrg. And there's also a companion draft on green networking metrics, and you see basically I'm presenting on behalf of a number of co-authors. Next, please. So the question, why green networking and why management for it? Well, I think everybody is aware that reducing the carbon footprint is one of mankind's grand challenges. And of course, networking applications have been a key enabler in this by reducing travel, by enabling remote work, etc. However, the question is this enough? And specifically, the issue is that networks themselves consume a lot of energy, and therefore net zero mandates that apply across industries and so forth will apply, and actually, in fact, are already in part being applied to network providers as well. So clearly something to think about. There are, well, various contributors to network energy efficiency today, and basically efficient usage of efficiency and so forth. There are, of course, general hardware advances, benefits from Moore's law, deployment factors. Do you basically deploy in a colder temperature and so forth? Advances at the lower layers, antenna technology, and so forth. Many of those factors are well, important, and they are big factors. However, they are kind of like outside what we in IETF and so forth could control. But what about network and management specific factors, and where basically IETF and IRTF could make a contribution? And so this, even if this may be a smaller aspect of the overall equation, and anything counts. So this is kind of like the motivation for this. Next, please. So in some observations, why I believe, or we believe this is specifically also a management topic, is for one, basically management in many cases involves questions of optimization already, right? So basically, you see many research papers on how do you place VMs, how do you place VNFs, how do you plan routes and segments and paths, optimize according to various ways, and always basically moderating different types of trade-offs which are involved. And well, in this, of course, well, energy usage and energy efficiency and so forth is yet another parameter that can be optimized, and that perhaps has not been so much the focus in the past, but really perhaps it should be. And also, in many cases, management involves control loops. I mean, I think RFC 75 was mentioned earlier, autonomic, right? So clearly you have a loop there, so you always have some kind of variation of that. You observe something, you analyze it, based on this, you make certain decisions, and then you basically act to modify it, and then the circle closes. And for those control loops, well, they apply clearly also basically to optimizing energy efficiency. And of course, short time scales are required, but one thing this basically sets up one of the drafts is one thing that is a common denominator in a lot of those things, regardless what your decisions or what your particular purpose is of the optimization, you do need to have visibility into what it is that you're optimizing. So you do need to have visibility into how energy is being used, how much energy is being used, and so forth. And finally, another aspect that we believe actually can be leveraged concerns the fact, and this actually makes it also more of a challenge, that communications is, or the incremental energy use in communications is not linear. So basically, when you think about it, basically when to transmit the first bit, you need to power up an equipment that basically creates, well, this requires, of course, a lot of energy usage right there. So basically the cost of the first bit is very high versus subsequent ones. Then basically if you utilize it higher, it really doesn't make much of a difference. And this suggests, the question is, of course, how to leverage and exploit that there are large potential gains, for instance, by being able to idling resources and taking them offline and so forth when they're not needed, and doing this basically in rapid time scales and so forth. So this is certainly one potential thing to explore to manage towards that. Next, please. So basically, in the draft, so the first draft concerns the problem statements or the challenges and opportunities. We decided to structure these challenges and opportunities basically into 4 different areas, starting basically with what you can do at the equipment or individual device level, and then looking at, okay, what could you do at the protocol level, at the level of the network as a whole, and then finally of the overall network architecture. Next. So at the device and equipment level, this is basically where perhaps many of the most obvious things immediately lie. Many of those aspects, of course, again, concern power-efficient hardware, eco-friendly materials, and so forth, important but outside IETF scope. Perhaps more getting closer is basically other, for instance, things such as energy-saving policies. This is very common in endpoints. You have power-saving modes, etc. But what about equipment inside the network? We don't really see much of that there. And the question is, what would those types of things look like? And then basically, and of specific interest, also in a prerequisite for a lot of things, is how do you provide visibility into the current energy usage? So basically, how can you even assess that and basically validate with whatever things, whatever aspects you are applying, whether, how well they actually work. And so basically this requires instrumentation inside the network. This is something that is relatively immediately, I guess, actionable, and it requires also energy metrics of the right types of energy metrics to base these things on. And I see Dane has a question. Do we take questions now? Or? I can do it at the end. All right. Okay. So then the next aspect concerns the protocol level. And this basically is the question, well, what can be done? Well, there are actually several aspects of this. So one thing one can think about, well, what would be needed in terms of protocol support to enable certain mechanisms or methods to save energy. So for instance, one of the things I mentioned earlier was, well, what if you could take, for instance, take resources offline when they're not really utilized? Obviously, there are controversies. What is it? Lead to a longer discussion, but assuming basically that you can do that, well, today one of the issues is it's often not practical due to the time scale. So if you take it offline and you want to take it online, a lot of time elapses when you find out that actually you really would have needed those resources for redundancy or for whatever type of reasons. And so the question is, well, what if those timescales could be dramatically shortened? And if you had that, you would still need to do certain things at the network level, right? You would need to be able to fastly discover what is the current status. You would need to be able to reconverge any state that would have changed at the network level very quickly, and so forth. And so these are things which potentially require thinking about what is required at the protocol level. Clearly, autonomics have a role to play there. Intent-based networking has a role to play there, and so forth. Second aspect concerns also for instance to think about such relatively, if you think about simple things to think about how can we make, for instance, the tables that need to be maintained in a network smaller. If you require less hardware, again, less state that you need to synchronize and pass around, presumably you would become more energy efficient. So this has questions of how do you address your network, how do you deploy, how do you partition the spaces. It's about with energy efficiency usage in mind. And then, and then there are many other aspects, such as, for instance, how could you, for instance, apply traffic adaptation that you basically maximize efficiency based on whether it's beneficial to have smooth transition, often good to avoid congestion and collision and so forth. On the other hand, sometimes, and I think we see this particularly in low power environment, it is actually beneficial to transmit bursty, so basically having some periods of silence and then basically transmitting it a bursty thing. And so all of these things are worth thinking about. Next one, please. And well, then at the network level, there are things to think about. Basically, then, well, if energy is a cost factor, or power efficiency is, well, are there, for instance, certain energy-related control protocol extensions that would be needed in order to, for instance, make SDN controllers or make distributed control planes and so forth aware of that and leverage that? Similarly, topics of energy-aware routing, energy-aware path configuration, which allow to assess, for instance, the carbon intensity one trip away or another of a path, and then basically optimize the network to minimize the overall footprint. For instance, to be aware to steer traffic among, if there are different alternatives, steer them along the one which is greener by some definition. Those are basically topics that are worth spending research on. Similarly, well, I was mentioning basically the issue of, well, what if we could, for instance, idle and take offline and online resources again? So this would be basically is a topic of resource weaning schemes at the network level. And then there are other aspects, right? So for instance, again, well, just like there's placement of virtual machines, the question of how do you place virtual network functions, for instance, again, with the power usage efficiency in mind, are going to there. And of course, for all of this, you need to have also green abstractions that apply to the network as a whole that also have a holistic picture.
Alex, can you speed up a bit? Time
Sure.
for question. Thank you.
All right. Okay. How much do I have? 1 minute?
Yeah, 1 minute will be fine.
All right. Okay. Good. So next, please. I'm almost done, I think. So one of the basically is one of the concrete first steps. Basically, is the companion draft to the challenges opportunity concerning network energy metrics, because again, it starts with providing visibility, and so basically there's this draft which defines basically attempts to set a define of metrics according to different, well, associated with different aspects, right? The related to the equipment, but also related to flows, related to paths, and related to the network at large. Again, this is maybe not so much a research topic, so more actionable. So perhaps this one doesn't belong into Nmrg, but I just want to put it here. Next one, and I think that's the last one. So yeah, so basically the intent here was to raise awareness and gain critical mass on this as a topic, and look for collaborators, also encourage more research into that area. And we're also looking for the proper landing spot. It seems that, at least for the research opportunities and challenges, Nmrg may be the right place. And for this, we would ask for feedback. So thanks. And
Hi, Dan Bogdanovich. There are two problems with energy and telecommunication. One is the optics. That's the biggest consumer in the networking today. And you cannot turn lasers on and off on demand because they take a few seconds to warm up and start propagating the information throughout the network. This is where majority of your energy consumption is. If you look at any of those nice boxes that the vendors are doing, if it's an optical box, suddenly the box weighs tons and uses kilowatts of power, but all that power goes into the optics. So that's an optical problem and material science problem that I don't think we are the right place to solve. But that is that is the major problem that has to be solved. And then the other stuff is you're looking for a new semantic to add new semantic to the routing, and that you are deciding, okay, here's how we will make new routing decisions. So your energy metrics there are the area, which ones are the right ones to use to make the routing decisions, and how to incorporate and how create the semantic that will take the energy routing into the account as well. You know, it doesn't mean that your shortest path is the best path from the energy perspective, because you have to know how your energy is being routed throughout the system and where is it coming from. So you have to create a much more complex semantic that we don't have the expertise as well. We have to talk to the energy distributors how they are doing that and how they have to route the energy, you know, in order to provide the demand for that. So it's a multi-structural problem. We can say that, yeah, we need the information from you to be able to make our decisions. And again, I don't think we should be finding, is there like an energy distribution organization that is looking into those problems?
So yeah, so very briefly regarding those comments. So first of all, clearly there are big. I try to indicate is maybe only a small slice that is within our control of this, and clearly, yeah, power consumption from laser AC is a big thing. But this, I believe actually this should not prevent us from looking at the things that we can control. But clearly, we need to know which ones we can control and which one not. Regarding the
but those are the foundations. If you can't control those things, then everything else that you can control is okay. Never mind. Sorry.
No, okay. So that's okay. Maybe this is so. I don't believe we should just give up, right? I mean, it sounds a little bit defeatistic what you're suggesting. If we cannot control the laser, we don't need to look at it. Is this what you're suggesting?
No, I'm not suggesting that we are trying to do some decisions without having the inputs from the material science guys as well as from the energy distributors, because you have to take both of those into the account to be able to make to create the right semantics that will be enable you to do the proper routing decisions.
Right. Yeah. But for the second thing, and I know we have limited time, I think, but very briefly, clearly there are many things that you can take into account, but basically making this awareness as an additional factor to trade off is a worthwhile thing to consider, I believe. And clearly there are many complexities, and it may not everything may be actionable that we can define a standard right away. This is precisely why I believe actually this is a good topic for IETF, because things of this nature may fall out of that.
Yeah. So just only quick question, quick answer if possible. Otherwise, answer offline, please. Okay. Thank you.
So thanks for your presentation. I think that the topic is needed, interesting, and relevant. While listening to your presentation, I was wondering something, and maybe it's a suggestion for you to move forward, right? Is how much, so if I want to transmit one single packet, I need to first build a set of network equipment, right? I need to actually build the thing, and then I will spend energy in lasers and so on. And I was wondering, what is the amount of energy it takes to build the actual network equipment? And maybe that's something that I know it's out of the scope of IETF, but I think that it is important to have at least to understand the scale, right? Is operation of networks 10% of the whole energy consumption of building a network and operating a network, or is operation just 90% of building the network, right, and operating it? Just a suggestion.
Okay, I agree with your observation. Okay. Yes, and clearly for a holistic thing, that should take that into account. And this is also a research topic, obviously, to how to optimize with that in mind.
Benoit Claes. So that's an interesting topic, right? To observe energy, etc. But I want to remind people that we had a working group called EMAN, Energy Management, in the past. It was about having power states in the network, exactly for what you were mentioning. It's Sunday, so I want to get a lower power state, or people are on strike or whatever. Now we put that in place. However, what happened is that whenever we look at the use case for network deployments, then there were no big use cases, from a money point of view. What I mean is that saving a port in a campus network is like 9 watts. So if you want to put all this in place for just 9 watts, what it's started to be interesting is whenever you could shut down the line cards, then we speak about big money. But then you enter in what you mentioned, the issue of the SLA. If it takes 30 seconds for a line card to comes up, then at that point in time, I had no operator who actually wanted to do this, because we are selling expensive stuff for which we're going to say you're going to put them offline for some time, and the SLA to come back whenever we speak about a couple of milliseconds of rerouting. It's not the same scale. So we were stuck at the use case issue.
Right, so I think the use case is clearly something to revisit. Actually, this is also a good segue for you to Charles's presentation, who I believe comes next, who talks about some of those past efforts. But yeah.
Jari Arko. I just want to say that this is very interesting topic, and we should work on that. I mean, it's obviously important for the whole society, and we should do our part. I just wanted to draw your attention to another activity that is coming up. The IAB is planning to launch a workshop on sort of environmental impacts of the internet and energy consumption and so on. Sort of has a broader scope perhaps than what you were talking about, but it's another venue where some discussions could happen. Also one-time workshop, of course, so it should not stop sensible research group and working group efforts elsewhere, naturally. But the idea is to have first of all, like a big picture analysis, like where is the issue, and draw in data center people and device people and application people and networking people, not just focus on our little networking protocols. Look at metrics, look at needs for new work where they would be most beneficial, and look for solutions. So that's the scope of the workshop. Announcement should come out after the IETF.
Thank you.
Sorry, Thomas Eckert. Yeah, so I think with EMAN, the best use case I saw was simply the PoE management, right? So using the network as the infrastructure to really manage physically a lot of interesting devices, cameras, lighting in building and so on, right? So there was, and I think still is, the whole evolving, new in-building network architectures, like, cheap switches that do lightning power everything under the ceiling. So I think that, still is something to be, taken much more use of, slowly evolving, right? So it's kind of these industries that operate in decades cycles.
Yeah, thank you. We have to stop here, and then you can start our presentation.
Exactly, that was the trick, right? So, all right. Okay, instead of looking forward, there's always a good thing in looking backward and trying to figure out what we have done so far. Next slide. So this is the third draft, and the name is down there. So, right, so the goal was kind of trying to for ourselves and hopefully in the community, get an overview of what the IETF has done for energy to enlighten the community, understand and how to apply it best, and of course kind of the users of whatever we have done in the IETF, developers and deployment. And then of course the stuff that Alex has started to present, look for gaps, close them, look for new areas, standards and research. And yeah, trying to also, market the IETF and its work in this area, whether it's for sustainability or what the example I was just giving, right? So all that stuff. For the draft itself, it seems to be most simple as an individual submission. If there's more interest, maybe we get some other form of sponsorship, but I think when you see the broad range of topics being covered, it seems like trying to run for IETF consensus on that content will make it rather less flexible for, you know, individual chapters with individual authors and good opinions to be brought together. We'll get to that, you know, call for participation later. Right. So, so obviously the IETF has never done anything for energy, right? So, oh, wait a second, there are these IoT low power networks. Okay, so we've done that. And oh, wasn't there one more thing and one more thing? So you really, when you start looking through all the IETF repositories from one area to the other, it reminded me of Monty Python's Life of Brian. You have to find that video clip which says, "What have the Romans ever done for us?" And it's kind of, yeah, pretty much everything, right? So, which obviously for energy isn't true, but it's really, when you see the next slides, it's a lot, right? Let's next slide. Okay. So the scope of the document is not only the things that people said were intentionally for energy and so on, but what I felt actually relates to energy, right? So a lot of stuff that is incidental. And that's really when you start thinking about what has the IETF and the internet done to impact energy consumption on the planet. And that is really pretty much everything that the IETF has done from the beginning, because it has led to what we now call digitization of non-digital pre-network workflows, which is really very much based on, you know, the foundations of the packet networking that the internet was the first and biggest one to explore in that respect, right? So from all the applications like mail replacing postal mails, group communication, then ultimately thousands of applications that were done without digital through HTTP, HTML frameworks, right? And so when you look at the success factors, then it's very much related through saving through scale, right? So the joule, the energy per bit cost has been going down because we have an architecture with the internet that is built for scale, right? If you would try to replace the internet with many, many parallel networks for different applications that were all smaller scale, you would end up with a lot higher energy utilization, right? So there are various aspects of the internet architecture, the IETF protocols, that have been contributing to this, you know, lowest cost, highest scale. The datagram with the multiplexing, the end-to-end transport. So I'm going through these, you know, architectural foundational parts of the internet architecture, relating them to the energy consumption. The convergence of network obviously being the most easy to understand, right? You started with data networks, you had separate voice networks, you had separate video networks, we did diffserv, we did inserv, we did all these things that allowed us to integrate these different networks. So we built a single network which was faster, ultimately using less energy for the same applications, right? And voice with SIP being one of the first applications that made that move after we had diffserv. Next slide.
Just if you can speed up a bit to make it in 2 minutes.
Okay.
I know this is a bit fast, but it just
okay. Sure. Yeah. So then we can go faster through this. So the energy saving through sustainability, that's another interesting taxonomy thing that we need to think about, because there are a lot interesting additional metric aspects we need to look into, right? So there is a difference between good renewable and bad energy that we need to take into account, and we also need to compare then the saving that we're getting to the pre-digital solution. For example, the fact that we've all been aware of that, you know, traveling in airplanes on the same amount of energy consumption is worse than doing the same thing on the ground. So that's where applications like collaboration, what we've been doing in the IETF ourselves, come in, and a lot of foundational technologies like RTC Web. Next slide. Okay, so then there's the whole, you know, page about exactly that low power lossy networks, where we have many, many working groups. So that is being covered. I'm not going to go through details to that. The higher layers of that are called constraint nodes and networks. Also, several working groups with good work on that. Next slide. And then there are specific sample technology enablers that even recently we had been trouble and opportunities to leverage, right? So sleepy nodes is a core technology to optimize through specific protocol operation the ability to run on battery or energy harvesting. And then my personal friend, or frenemy in this case, IP multicast. So those technologies are covered. Then the energy production consumption management network, smart grid, and the even more cool use case of the synchrophasor network. So those are the networks built for the power generation and consumption. So that is being covered. Next slide. And then the EMAN, we mentioned that. And finally, the power awareness in forwarding and routing protocols. That's what Benoit mentioned as where we stopped, because we kind of didn't have, you know, I think the tool set to go further. I think we have some of that tool set now, so we can look into it again. SDN or some of the anima work that we've been doing, I think will help a lot for the resilience we need so that we can low power networks better. There's just a little bit of the gaps. I mean, this is just trying to capture what we've done, not what hopefully we can do. So next slide. Which really brings us to, you know, the call for action in terms of please read it, comment on it, and even better, so contribute to it. You'll see a lot of chapters where you may be the expert of any of them, or you may be missing chapters. So hopefully this can become a community effort. We can get a mailing list if the one that we've just randomly been looking for is not the best one. So there's this old reducing energy consumption with internet protocol exploration called Recipe. And so that might be good mailing list to revive after it's been dormant for 10 years, because that was about the time when we stopped doing all this good work and start discussing energy related work again. But of course, Nmrg, everything needs to be managed, right? So that's why such a broad topic is I thought from our perspective, very good to be, you know, it's the new vertical, you know, for all of management, right? So we had security, we need to manage it. Now we have energy, we need to manage that. So it's also a vertical topic for this group. Thank you.
Thank you very much. So question and comment will be taken offline. Next presentation.
Good morning. Nice to meet you. My name is Yonggun Hong. I'm working for Daejeon University in South Korea. So first, thanks to give a chance to present. Next page, please. Yeah, this is the history. From last meeting, we submit the document, but at that time, we don't have a time to present. So this is the first time to present. Okay, next page, please. Yeah, this is the motivation. So as I know that many persons have some interest of the AI and AI technology, but as experts of the network and telecommunication, it is not easy to find item for standardization. And there are some change in the AI area for especially the deployment AI services. For example, in the before we are focusing on training, running, but nowadays we are focusing on inference prediction. So if we think about the inference, not only high performance server, but also small hardware, microcontroller, low performance CPU, and the AI chipset, the optimal target device. The reason is the cost. So if you utilize the high performance server, okay, it is good, but the cost is very high. So if you think about the cost, we are also think about the low performance, the hardware. So if you think about configuring of the system in terms of AI inference services, then you consider various kind of things. For example, if you think about training, then the point is to accuracy of the model. But if you think about the inference, you consider which is the target device. For example, it can be local device, edge device and cloud server. And if you find or if you judge the objective the system, then you can consider and you can adjust the objective, for example, accuracy and latency and network traffic and resource utilization, etc. So in this document, we show some configuration of the system, for example, AI model. If we think about AI model, there are very kind of the AI model. For example, heavy and very size of the AI model. It represents the high accuracy of the model. But in some point, you can think about the lightweight AI model. The model size is very small and the inference time is very short. There are pros and cons. And also another consideration is the serving framework. Okay, you can utilize the web framework to provide AI services, but nowadays, for example, TensorFlow serving, TorchServe, that is the targeting framework for inference system. So you can utilize AI web framework or specific serving framework. And communication method, for example, REST, or you can utilize gRPC and design device capacity, for example, CPU, RAM, or the capacity of network interfaces and inference data. So the main reason is of this document is to accelerate the study AI issue in the Nmrg and IETF. Okay, next page, please. Yes, this is a generic procedure of AI services. So I know that many persons are very familiar of this generic procedure. The first step is to collection and store data, and the next step is to analyze and pre-process of data, and the next step is to train AI model, and another model is to deploy or inference AI model, and the final step is to monitor and maintain accuracy. So the focus point is to red box, the deploy AI model and monitor maintain accuracy. So if you think about each step, for example, collection, store data, and analytic pre-process data, the device can be sensor or DB or AI server. So if we collect the data, the internet or network could be used, but in the trained AI model or analytic pre-process data, then there are no connection with the network. It can be done only local server, local area. But if we think about deploy or inference AI model and monitor and maintain accuracy, then I guess that there are something to do for the point of the internet, for the point of the network, because we can utilize, we can deploy this system in a distributed approach. Okay, next page, please. Yes, for example, you can set up your network configuration to provide AI services. The first figure is done, it is only done in the local machine, local server. So the client module for AI service request to the server module for AI services, it can be done in the same machine. But if you divide this action in the second figure, you can put the server module AI services in the cloud server. Then you can ask the AI service to the server module in the cloud. So in this case, there's some network, there are some communication issue. And the third figure is to AI inference service on edge device. Yes, the second figure and third figure, there are same and different points. For example, in the second figure, the AI inference service on a cloud server that utilize the high performance server in the cloud, but in the third figure, AI inference service on edge device, they utilize a little light or small device in the edge network. So it is the difference. Next page, please. Also, you can utilize at the same time cloud and edge device. So nowadays, we call it task offloading from the edge and cloud area. Okay, next page, please. Yeah, this is the main point of this contribution. So until now, if we think about the AI services or AI system, the main objective is the accuracy of the model. But if we think about cost or performance, then not only accuracy of a model, but another point, for example, latency of services or network traffic and resource utilization are also important points. So to satisfy this objective of AI services, then we must consider point is to AI model. As I said that there are 2 or 3 kinds of the model. For example, heavy AI model or lightweight AI model. So if we use heavy AI model, then accuracy is good, but the latency time is not good. There are pros and cons. And if we, the second point is serving framework. As I said, there are 2 kinds of the serving framework. Then one is the web-based serving framework, and the other is to serving targeted, for example, TensorFlow serving or Torch server. Yeah, I think that a good solution is to using serving targeted serving framework. But if you utilize serving framework, then there are some requirements. For example, high performance CPU or high performance hardware. So also there are pros and cons for regarding serving framework. And the other consideration is communication method. I know that many persons are familiar to REST or gRPC in the AI system. So if you utilize the little big data, then it is better to utilize the gRPC. Yeah. And the other consideration is the machine capacity. For example, CPU, RAM, network interface, etc. And the final consideration is to inference data. For example, the data is related to real time, or the data is related to batch, or the data is secure, and or the data is non-secure. So I think that there are other considerations to deploy AI services, but now we are trying this kind of consideration to implement AI system. Okay, next page, please. I show you one example of the AI system for object detection services. I guess that this can be utilized to autonomous driving. So in the left side, this is the machine requesting AI services, and the right side is the machine performing AI services. Yes, you can utilize the 2 modules in the same server, or you can divide this module in a distributed, so the right module can be located in the server or edge, etc. So you can change this configuration by changing your IP address or port number. Okay, next page, please. So in this case,
can you conclude in 2 minutes, please?
Okay, this is the last page. Yes, this is one of the experimental results of our object detection service in each services. So as you can guess, in the experiment in the cloud server is very good. The average time is to 0.5 seconds, but yes, this is the latency time. So the edge device is not good, and the local device is also good. So this is only one example of the latency, but if you think about accuracy or network resource or resource utilization, you can many cases to combine for example, to consider which item is important. Okay, next page, please. Yeah, so right now I want to ask the movement because it is the first and rough version. So it is the initial version. So I hope in next meeting, we will bring enhanced results and share our result and our understanding with yours and promote some the activity in this Nmrg. So that's all.
Thank you, Jungen. So we have to move on. And so for a question and comment will be offline.
Okay, thank you.
Okay. Okay, well, I will give now a quick update on the document about the research challenges of coupling AI and network management. So as you know, it was before shared a Google document. So these are already different iteration, but here's a zero version of the draft. So next slide, please. So basically, what we have done so far, we have of course transformed into the right format, of course, with the help of 5 key people that you have seen on the previous slide, actually. Because at the beginning, there were a lot of contributors that are listed in the acknowledgement, of course, but we need to shorten a bit the main editor team. Of course, we integrate different feedbacks that you already received or the previous version. We change a bit the title as well, also to include both let's say, the 2 ways of AINM and network management. And although we identify there were some challenges that we have identified to be important, where there was no content, and so we had the content now. Next slide, please. So here are the major edits. So basically, we had a new constraint regarding how we can, let's say, identify what characterize a difficult problem network management, and what type of constraint. And certain constraint is more characteristic was able to have more time-efficient solutions that we extended to be more cost-effective solution in general, not only time-efficient. So all type of actually cost can include also energy, of course. We also extend the description of possible scenarios, and yeah, major update regarding challenges was we had these challenges to have the human in the loop when using AI in the context of network management, of course. Next slide, please. So here just a summary of the current document. Of course, you can see there are these 3 main categories of challenge. The first one is AI techniques for network management. Second one, network data as input for machine learning algorithms. The last one is acceptability of AI. So the 3 categories with sub challenges that we identify. Next slide, please. So what are the next steps? So of course, as it was already with different iterations, the document somehow is quite mature. But of course, we also still need your feedback. We have already identified some changes that you have to be done, in particular regarding distributed AI or collaborative AI and the integration of lightweight AI. There are some discussion within, let's say, the editor team about regarding to highlight a bit more the different types of problem regarding the type of data in terms of labeled or unlabeled data, knowing that maybe in network management we have more unlabeled data. So that's also something that we have to keep in mind while addressing, let's say, using AI in our domain. So there's some discussion of adding some legal or regulatory aspect about the use of AI. Of course, again, in the context of network management and networking. And so, no, yes, we are requesting your feedback, maybe norm and the mailing list, but of course, we have some question regarding the value of the document in general for the group, for the community. The format of the document, do you think in terms of presenting the different challenges and what are the important challenges and maybe gaps? Is it right or not? Do we have missed something? Although this is very important for us, you say we miss a very big challenge, and also the granularity, because it's hard to have something kind of exhaustive regarding the challenges to cover everything. But of course, we don't want to dig too much into a technical level. Again, we don't want to add something specific to a use case or something like that. Should be quite general. And that's it for so I don't have the time.
Thomas Graf from Swisscom. So first of all, thank you very much for the document. I think it's very important, and speaking as a network operator who is collecting a large amount of data from the network and also developing anomaly detection, I'd like to get feedback on section 7.2 and 7.3. I recommend to do references on RFC 9232, which is the network telemetry framework, and especially describe a little bit regarding network data modeling. And for the anomaly detection or AI ML part, I suggest to reference to the data mesh architecture, which is nowadays currently being used in the industry. And there, especially on source aligned data, so preserving the format from the network, and also aggregates. Aggregates helps to reduce the amount of data. And for machine learning and for AI, and maybe also add a section on that, especially when you do real-time processing of data. Not all the data is there at the same time, so that imposes also challenges.
Okay, yeah. So nice. So if you can just drop you an email with the different references, so it will be very
perfect.
Very nice. Thanks
you.
a
lot.
Thank you. That's it. So now we have our last presentation of today, which is on network measurement intent, an IBM use case, and I think the presenter will be Gihan.
Hi, chairs. Can you hear me?
Yes.
Thank you very much. So since the last interim meeting, we have started calling the procedure of calling for adoption of the draft, and we have received some valuable suggestions. So next slide, please. We received about a total of 8 members agreed. So many thanks to you guys. And we also received many valuable questions and suggestions. So due to time limitation, we will not cover all of them in this presentation. We'll just take a few of them for example. And if you are interested in the draft, you can read our updated version on data tracker. So the first question is regarding about the sampling rate. So the sampling rate will be constant or will be constant or changeable due to different requirements and algorithms. The second one is about how to ensure that the measurement resource meet the requirements. So in our IBM and NMI system, so the measurement result will be ensured by the closed loop verification. The assessment module will determine if the result is acceptable and give the feedback to the policy module to modify the policies. So next slide, please. And the third question is about the difference between static NMI and dynamic NMI. So we have made a clarification on different terms. So a static NMI means the measurement is independent of the network state. Let's say that we want to measure the network delay of the packet, and the IBM system will continuously sampling whenever the network behaves. And but in contrast, the dynamic means the measurement is corresponding to network state. For example, we want to measure the network delay of the busy time. The IBM system will determine whenever the system is busy and adaptively change the sampling rate when it detects the network state seems to be busy, and it will report us differently compared to static NMI. So the last question is about will it be about the policy if it will be changeable. So like the question 2, so in our NMI system, the policy execution will be closed loop, and it will be assessed to tell the policy module to modify the different policies. So next slide, please. We also made add some relative references to the draft, and also we have modified the figures and some improper writing problems, and all of these has been updated in the draft. So next slide, please. So for the next types of the draft, we still want to say that these NMI draft can be seen as one of the IBM use cases. So if you have, we are very welcome that if you have any good ideas on our draft, or if you have another separate IBM use cases, we are open and help very welcome to merge them into into a total into one single IBM use case draft. So we're looking forward to your comments and suggestions. And thank you, guys. Yeah, that's it.
Thanks a lot, Kian, for sticking to the time and also the consideration. I think it's quite late in your area. So thanks, everyone. We are reaching the end of the meeting time today. I think we covered a lot of topics. I really invite everyone to continue commenting after the meeting, if you meet each other, but also using the mailing list or contact the different participants of the research group. I think this is also very important to continue the activity in between meetings. So thanks a lot, everyone, and enjoy the meeting. And thanks for our remote presenters. Goodbye.
No, this I didn't remember.